Welcome to another gas laws video. In this one we are going to take those separate gas laws that we looked at and we're going to combine them together and see what use that is. Don't forget we've got this core model of things that are particles, and in fact we are going to refine this a little bit because in this image we go from solid to liquid to gas, and you can see that the bonds change a little bit, but it's still, that picture of a gas here doesn't meet the requirements for what we're going to be talking about. We need those particles to be of negligible volume, so we need them, instead of to be nice little circles like that, we need them to be points. That's our first assumption. Our second assumption is that they're all equally sized, i.e. points, and have no intermolecular forces, so there's no interaction going on between them at all, and there's not really an interaction other than the elastic collision between them and the walls of the container. We need them to move, as our assumption number 3, in entirely random motion, very much the Brownian motion that we have talked about in the introduction. Finally, we need them to have perfect elastic collision, so no energy lost from the system. And so those are our 4 assumptions for the gas laws. We looked at Boyle's, Charles and Amonton's law, or the Guy-Lussac law, how pressure and volume are linked, how volume temperature are linked, and how pressure and temperature are linked. So you can combine these in a very straightforward fashion, give you what's called the combined gas law, and this is actually very useful. It's not in a lot of specs because they often go straight for the ideal gas law, but this is still very useful in order to manipulate things. It's really important for our students to have a good understanding of how all of these things are related. What we need in order to get to the ideal gas law is Avogadro's law, and we often kind of miss this and we just pull in the Avogadro bit, but it's worth stating explicitly, I think. He says that if you've got equal volumes of all gases at the same temperature then and the same pressure, then they'll have the same number of molecules. So in essence, the same number of things would give you the same change in momentum on a collision to give you the same force. And it doesn't matter, here I've got hydrogen, helium and carbon dioxide, for example, and they would all follow this law. Written mathematically, it looks a little bit like this. And that n can be the number of molecules, or it could be the number of moles, because if you remember, the number of moles of a gas is just a number, it's a number of molecules. So then, our cast looks like this. We've got Boyle's, Charles, Amonton's and Avogadro's law, and you can see straight off the bat that it should be reasonably straightforward to combine these. When you do that, you actually you get a PV equals n T kind of relationship. We need to pull in a little bit extra. We need to pull in this we need to put it like this in order to express this equation in a way that allows us to use moles instead of the absolute number. So P here is obviously pressure in pascals, that's the SI unit. A couple of things to look out for here. It's quite often given in kilopascals and your students will miss that. Very occasionally, if you're working from old examples, it might even be in atmospheres, and a standard atmosphere is an awkward number. It's 101,325 pascals, and so that's quite awkward. Volume here, again, your students may trip up. Remember that a meter cubed is a lot of millimeters cubed. Okay. It doesn't scale in the way that students sometimes want it to scale. So 1,000,000 centimeters cubed, for example, is a meter cubed. So in this then, in our ideal gas law, n is the number of moles. So remember that's just a number. It's a very big number, but that's the number of molecules of carbon in 12 grams of carbon 12 isotope. So then we've got R, and R is a gas constant. It's a number that makes the mole bit, the rest of it, all fit together and work. You can look it up. It's 8.31441 joules per Kelvin per mole. It's a bit of a mouthful. You sometimes come across this in different units, for example in atmospheres or those kind of things. The temperature is in Kelvin. Now, we haven't really talked about Kelvin, but Kelvin's is an absolute scale of temperature. Unlike all of the rest, which are relatively arbitrary, they start and finish at points that we've just chosen. Kelvin has got a very fixed point. Kelvin starts at what you call absolute zero. So if you look at this, you think actually this equation implies that if you keep reducing the temperature, the volume and the pressure of a gas must keep decreasing, and at some point you must hit zero. And so that's what this is all about. This is what absolute zero is about. If you explore the gas laws, and it's one of the lovely things that you can do with your students, you can plot volume against temperature for a gas or for a nearly ideal gas, and that will extrapolate back to the x-axis at a point which is about minus 273 degrees Celsius. So your conversion factor between Celsius and Kelvin is that figure of minus 273.15 degrees, if we're being extremely precise. They share a common point at the kind of triple point of water, but obviously it's shifted by that same figure each time. So the gas laws are fantastic. They're a brilliant, the ideal gas law is a brilliant model, and it serves us very well. You can break it a little bit, and that's a fun thing to do. So this here is a thing called the Hyman fire piston, and it actually leads you on to the next step beyond the kind of ideal gas law, because in this particular case I'm going to reduce the volume and increase the pressure of a gas, and I'm going to do that very, very quickly. And so I've actually raised the temperature enough, I'll show you that again, raised the temperature enough to ignite the small piece of cotton wool in the bottom here. And so if you just look at it from the gas laws perspective, there's something funny going on, and it's actually because I have to slam that piston down very hard. I have to do a lot of work, and that energy goes somewhere, and that actually raises the temperature of the gas. And so we're into the idea here of doing work, and the fact that we can do work and have that linked to the gas laws. And that's where the application of all of these things come in the heat engines. So here in the middle is a heat engine running. This is a thing called a Stirling engine, and it is sat on a boiling mug, or rather a mug of recently boiled water. And the temperature difference between the bottom and the top of that is, if you think about it, a kind of potential difference. And so this thing is causing there to be a transfer from the thermal store of the mug into the thermal store of the air, and it's exploiting that difference in order to cause there to be an increase in the kinetic store of the little flywheel in gold there. Heat engines are huge. The reason why there's a picture there of a lovely sunrise that I took it a couple of days ago is because the atmosphere itself you can think about in terms of a heat engine. We're looking at we have a kind of a heat source of the sun, and we have all of these fantastic atmospheric processes going on because of the kind of potential difference, if you like, between the coldness of outer space and the heat of the sun and our Earth rotating around and having these kind of temperature differentials between the equator and poles, and also the day-night temperature differential. So onshore, offshore winds, all of that kind of stuff, the trade winds, that all of that is driven by kind of gas law and heat exchange, and all of that is modelled in this fantastic way. You can model it very precisely with your ideal gas law. Thank you very much. See you next time.